Hi, everyone. I'm Anish Sheikh with the Google Global Networking team. Today, I'll be talking about the work that we've been doing over a few years, actually, on building a multi-layer network model to represent all of Google's production and non-production networks. This talk is based on largely on a paper that we published recently in this year's NSDI conference. And there's a link in the slides. Urge you, if you're interested, to get some more details to go have a look at that paper. It has a lot more detail on some of the things I'll be talking about today. As I said, we've been working on this for a few years at Google, and we think we've made now enough progress that it's worth talking about to a broader audience where hopefully it might benefit others. So we've organized the talk along sort of three main sections. I'll try to give some motivation for why we think we need a common structure for representing the network. And then some of the design choices that we made in building out the network model, including some of the surrounding infrastructure. And then I'll try to save some time to talk about some lessons and experiences that we went through, some of them painful, in doing this work that other people who are interested in also modeling networks may find useful. So just to help motivate the reason why we need a network model, we can start by looking at kind of the size and scale of the networks that we're working with. So this is an outside-in view of Google's network, our cloud network. It has a little over 130 POPs around the world, terrestrial and subsea cables around the world. So it's a large global network that we use to deliver all of Google's services and our cloud platform. And then if we kind of flip to the internal view of Google's production networks, this doesn't include, for example, our campus or office networks. We can sort of build it up this way. So we have our data center fabrics. These are big multi-stage CLO networks. We've talked about them in other forums. This is basically our Jupyter data center fabric. We have a WAN that interconnects all of our data centers. We call it B4. It's a software-defined network that we use to interconnect data centers. Then we have another WAN that connects basically all of our data centers and regions out to our edge. So this is our user-facing WAN. We call it B2. As part of B2's edge, we have peering metros where we've implemented another SDN architecture called Espresso that we've also talked about in other forums. And then, of course, we connect to the internet at these peering locations, and this is how we get to users and enterprise. So you can see there's a number of different networks here, and this doesn't even include all of the networks that we run, but these are the major production networks. And so we, of course, are interested in driving automation and virtualization. So we also kind of include in that our virtual network. So our cloud runs the Andromeda virtualization stack, which we've also talked about separately. This is a layer on top of our infrastructure that implements things like virtual private clouds as part of the Google Cloud Platform. So as I mentioned, automation is sort of a key requirement for all networks. I think we've talked about it in NANOG over several years, and lots of important reasons for automation and motivations. Obviously, one around scale, being able to grow the network without necessarily proportionally growing our engineering staff. Automation is an enabler of that. Being able to deploy and stamp out designs and configurations in a consistent way to avoid introducing snowflakes into the network is another key motivation for automation. And then, of course, well-programmed automation makes fewer mistakes typically than human engineers do. So the correctness of repeated actions and so on can be improved through automation. And we often think of automation as being targeted at things like device turnups or link turnups, configuration updates, using automation to set up monitoring or probing, using automation to help us collect data to troubleshoot the network when things go wrong. But as you get to sort of larger scale, you see that we need automation in a bunch of different aspects of managing the network, including things like early stages of a network design in terms of forecasting and capacity planning. turning those plans into, maybe an abstract design and then a more detailed network design, figuring out what is the set of physical infrastructure that we need to order and deploy. We use automation also for informing the work that human engineers are doing, for example, on the data center floor when cabling a new data center fabric, by providing them the information that they need in an automated way. And then, of course, things that we mentioned before around configuration and monitoring and troubleshooting diagnosis. So automation is key, but to do automation well and safely, uh, we need precise and accurate data about the networks in question. So, for example, we need precise data about connectivity plans at the abstract layer. So, for example, you could imagine, a model that captures information that is sort of the 12-month connectivity plan for capacity between various metros in the WAN. A separate connectivity plan that reflects the existing network that's sort of fully concretized in terms of devices, line cards, links, configuration, all of that. And then you get into further details that are represented in the model that enable an automation around things like device and software controller configuration, access control policies, routing policies, all the way down to IP address allocation and assignment that's captured in the model. So we need automation basically we need data rather to kind of drive automation across all of these different stages of the network design and deployment. So that brings us to kind of the design of our network model. So we call it multi-abstraction layer topology, or MALT. We have a separate name internally. This is the one we're using externally. This is Google's internal sort of standard network representation for almost all of our networks at this point. So it's taken us some years to get to adoption across all of these different network environments, but now it's sort of part and parcel of all of the networks that we run, or nearly all of the networks that we run. So it includes both, I would say, network topology, connection of nodes and links in the network, as well as what I'm more generally referring to as structure, which is kind of more abstract information about the network, including things like configuration and in some cases operational state of the network as well, are all included in our network representation. Sort of the main function that it serves is interoperability between all of the different automation and software systems that we have. So having this common standard lets us build software that basically works against that standard, and then any producers and consumers can use the same format to exchange data. And I'll say a bit more about that in the next slide. It supports multiple layers of abstraction. So the model contains things like, buildings and racks and even conduits, all the way up to, virtual abstract links and virtual networking layers. So it sort of spans all layers in between as well. We've had to figure out how to make it extensible and evolvable. This is something I'll talk a little bit more about later. As new use cases arrive, and they come all the time, as far as use of the model, being able to extend the schema of the model and evolve its ability to represent various concepts and structure is key. We've used it to implement network management systems that employ things like declarative network configuration. I'll give an example of that. To be able to really make good use of it and to drive wide adoption, we've had to build a fairly extensive software ecosystem to support it. So it's not enough to just define the model and the schema. There has to be a rich set of software around it to make it usable and useful. Okay, so a little bit more about why we need a standard representation. So before we had MALT, it's not that we didn't have models before, it's just that they were very bespoke to certain interactions between producers and consumers. So there's sort of bilateral agreements between a producer and a consumer as to how data would be defined and exchanged. And a lot of the information about the structure of the network was hidden in code. So obviously a standard representation gives us this decoupling of producers and consumers. So we try to capture all of the knowledge about the network in the data in the model itself, rather than having it sitting in code. And this allows us to also build a bunch of shared and common infrastructure, which is sort of a key efficiency around that single standard. So we don't need to then build additional, very similar looking capabilities around n different standards for the network. We can sort of focus on the single standard. So this is a large motivation for sort of driving adoption of a single common network model across all of our networks. So when we started this work, one of our main use cases, or maybe the main use case, was around building an intent-driven configuration system. And the reason why the model was so key is that the intent API that we had in mind here really was all about manipulating the model in order to drive configuration in a zero-touch fashion of the network. So this architecture sort of proceeds like this. We have a bunch of workflows. These are workflows that are doing things like device turnups, provisioning a new BGP peer, external peer, maybe adding capacity to a link. And they work against this intent API. And the intent API is basically an API that allows the workflow to manipulate or update a model of the network. And then that model is used by the configuration generation system to basically generate the configuration needed to realize those updates. And then they're finally validated and pushed to the network through an orchestration and config push block as shown here, and also probably stored in a config database. So the network model was the thing that allowed us to build this intent-based system where instead of directly manipulating device configurations, we were having workflows manipulate a model. It gives us a chance to validate those changes using the model, and then have a representation that we could test before we actually push to the network. And then once we had the model, a number of different use cases became possible. And it's perhaps no surprise, we started doing things like using the model to implement various kinds of health checks. Maybe they're health checks around, BGP sessions being up, or capacity health checks to make sure that capacity that has actually been provisioned and then drained for some reason is, undrained correctly and in a timely way. We use the model to set up all of our device level monitoring. So to understand which devices are there, which devices are actually appropriate to monitor is all captured in the model. We use the model to figure out, which peers are in sort of which different classes that we have, and then use that for managing those peers. And then we've introduced, of course, additional stages of the life cycle to the model. So we started out with this model being primarily about the current state of the network. Think of it as sort of the as-built network, if you will. But then as we started thinking about using the model for also planning future versions of the network, we added additional versions of the model to use for things like planning and high-level design. So some basics of the MALT design. We use this notion of an entity relationship model. So, this shouldn't be confused with a relational database. But if you're familiar with sort of database terms here, so an entity relationship model is basically a way to represent things that might be real or abstract. Entities have a kind and they have a name. Entities have sets of attributes, which I'll talk a little bit more about. And then we use relationships to interconnect entities. Our relationships don't actually have any attributes themselves. We capture all of the information within the entity, and then the relationship just tells us how these entities actually go together. So some examples of these, real or concrete entities, things that you might expect, like routers, transceivers, fibers, machines, buildings. And then we have abstract entities, like an entire multi-stage clone network, an entire Jupyter fabric, in other words, maybe a group of links that comprise a trunk. And then we have lots of grouping constructs of all sorts that help us manage and reason about the network. And then some example relationships are things like a contains relationship. This is something we use quite often. Things like a rack contains a device, or device contains a line card. A network might contain another type of subnetwork. Another relationship we have is aggregate. So this is used for things like link aggregation is the canonical example there, where an aggregate link has an aggregates relationship with its component links. Control relationships. So in an SDN network, for example, we have controllers that have a controls relationship over the network that they're responsible for. configured on is another example. So we have roughly about 250 different types of entities defined today in the model, and around 20 relationships. And I'll talk a little bit more about our kind of approach to how we grow, or how we think about growing the set of entities versus relationships. So here's a kind of trivial example. It's trivial in what it's trying to represent, but the example will end up not looking as trivial, and I'll explain why. So this is basically trying to represent a single layer 3 link between two routers. So we have the EK stands for entity kind here. So we have two entities, routers on either end. They each have a contains relationship. This is the green arrows with interfaces. So they contain this interface. This interface has an originate terminate relationship with a logical packet link. So we use logical packet link to represent sort of L3 adjacency. And you can see that this is sort of how we represent entities and relationships. So the relationship, as I said, is the contains picture here. And then if you build out the rest of this model, you can see that we have an additional logical packet link because we represent links as unidirectional entities. So we have two of them for every adjacency. We also may want to represent the layer 2 adjacency, which creates a relationship between the interface and the port that it traverses. It uses a traverses relationship here. And then those similarly have originate terminate relationships with another entity, which is called the physical packet link, which represents the layer 2 adjacency. So we have attributes in each of these entities, which I'll give an example of, and then these relationships are sort of bare in the sense that they just capture the relationship, but no attributes. So we need all of these entities and relationships, and this isn't even the full set to capture a single layer 3 adjacency. And so you might think, well, boy, this looks pretty complex and too verbose. But I guess the rationale is that really what we're building are systems that enable us to build software to kind of help automate the configuration and management of these things. So, we know that computers are really good at processing large-scale graphs with potentially millions of entities and lots of relationships, but software is really poor at figuring out what's actually going on. You have to be super explicit, provide as much detail as needed to get the right outcomes. An engineer looking at a graph with some missing pieces can probably reason about what's missing and what's needed, but computers can't do that. So hence, we have focused on making the model as explicit as possible to enable software to kind of operate on it. And then we do have ways to represent these entities and relationships in text so that engineers can read them when we have to. But this isn't the normal way that we actually operate on the models. And the text that I'm showing here represents about 80% of the previous diagram, so it doesn't capture quite all of it, but it captures quite a bit of it. Here's another example of a DWDM system. If you're familiar, these things have multiple layers of abstractions with different types of abstract links from ODU down to OMS and OTS. Our optical transport modeling captures things like terminal optic systems, amplifiers, ROADMs, all the different sort of fibers in between, as well as these abstract links. So the abstractions are pretty extensive and detailed, and this is a good example that captures that. And then the last example I'll show is, this is a simple switch topology where instead of a router, we might have a packet switch entity. It has a couple of layer 2 ports that are, again, using the physical packet link to represent adjacencies. And there's also ports that are part of a machine, maybe through a NIC, for example, and the machines are connected into the ports on a switch using the relationship shown here. This is not that dissimilar from the L3 example. It's just another example at the switching layer, including things like machines and server ports. So as I mentioned, entities have attributes that give us a way to express what the intended configuration and properties of that entity are for different points in the topology. And then we also have a way to represent some state variables as well. So this is a partial example for a port and an interface. So the port is on the left and the interface is on the right here. The red box captures the intent attributes, things like names of the ports, address assignments for V4 and V6, maybe the physical capacity that's intended on that port. And then there's some observed attributes that might represent operational state. These are things that could include things like packet drops that have been observed, for example, populated by a telemetry system. So a little bit about the software ecosystem. This, as I mentioned at the outset, is a very important part of Malt's usage and adoption. So we don't really get that far with just the entity relationship model and the schema or the definition of entities and relationships. We need a way for software to actually use the models. So we built a fairly extensive set of libraries that support some common operations in terms of traversing the entity relationship graph. Abstracting some of the details out for consumers that don't need them. We have a way to auto-generate documentation from the schema. Oftentimes, if you're new to the model, being able to go quickly to a web page that has up-to-date auto-generated documentation about what the entity does, what relationships it supports, etc., is very useful. We have some user interfaces that allow visualization of an entire network model, as well as of a particular schema. Things like, we call them signature graphs, that show the kind of key entities and relationships that are represented in a model without necessarily showing all of the instances of them. We've built a domain-specific query language. By domain-specific here, I mean that different network environments have different kinds of query requirements, and so we have built a query language that runs across them. But we have notions of things like canned queries or predefined queries that are maybe specific to a specific network. And then we have, of course, a storage system for all of these models that we've defined that is sort of a key part of the infrastructure and is a common piece across all the different network models that we use. So a little bit about queries. These models tend to get very large, as you probably can guess looking at the earlier examples. And most applications, let's take, for example, an application that's trying to build a configuration for a particular device or maybe a particular protocol. Obviously, that application doesn't need the entirety of the model to be able to generate configuration for that device and its associated interfaces and ports. It just needs basically a subgraph. So we basically build the query language to allow retrieval and traversal of small regions of the model rather than the entire graph. And as I mentioned, we have a query language that makes this reasonably efficient. It's still fairly complex, I would say, not necessarily the easiest thing to learn and use, just because it's hard to get the balance right, we found, between how expressive the query language is and how usable it is. So this is where the canned queries have come in. So when we find a set of common queries that are used often by software systems, we try to build those as predefined queries or parameterized queries that can be easily run by the software. And the canned queries also are more durable. So even if we change the schema underneath or move information in the model, the canned query can sort of stay unchanged. And so the software, of course, stays unchanged while it still works with the model. Of course, we have to change the implementation of the canned query to handle the schema change. You may be wondering why we didn't just use SQL for these queries. One of the reasons is that we do have a SQL database underneath. So the storage system is designed on Spanner, which I'll say more about, which is a global geo-distributed SQL engine. But we decouple the Malt schema from the underlying SQL schema. And this allows us to also have clients only worry about the Malt schema and not have to worry about changes to the SQL schema in case we make modifications to improve, for example, efficiency of how things are stored, which we have done. So a quick thing about storage, as I said, we call this Malt Shop in the paper. Malt Shop is a single service, so we don't build multiple storage systems. We've built a single storage service for storing all of the Malt models that we have across all of our networks. So it's one high availability service. It promotes sort of the sharing of models between systems. In other words, it acts as sort of a central clearinghouse of all the models that we've defined. And it ensures that we have one place to go and find models that you may need. So Malt Shop has support for many, we call them shards in the paper. You can think of them as essentially just models. So for example, we have a model of B4, we have a model of B2, we have some models that are joint across some of these things to enable systems that need to reason about network structure that crosses some of the network boundaries that we have. The models have their own access control associated with them, and they also have immutable versioning semantics. So in other words, when you make a change to a model, it creates a new version of the model using a copy on write mechanism. So it's sort of space efficient, but it gives you an easy way to sort of track changes using versions as they're generated. As I said, efficient support for incremental updates. We use Spanner underneath the covers to get a scale and geographic consistency. So we solve some of these hard problems in terms of consistency and global scale roughly for free, in the sense that we're just building on top of a system that we have. And currently we store thousands of models in MaltShop, each with millions of entities potentially, and handling thousands of QPS. So in the last part of the talk, I wanted to spend a little bit of time talking about lessons that we learned. I'll just quickly go through this list, but we'll spend a bit more time on just a few of them. Schema design principles. I'll say a bit more about this, as well as schema evolution and using design pipelines. As I mentioned near the beginning of the talk, we use different models for different phases of the network. So there's the notion of, for example, of an as-built or as configured network, and then we have networks models rather that are used in the course of planning capacity, planning the design, high-level design and low-level design. And these are separate models altogether. They use the same schema elements in many cases, and they may use different schema elements to represent maybe more abstract entities, as opposed to like the configured model, which has a much more concretized version of the network. The challenge of migrating users as we change the model schema, we consistently learning about how better ways to model things, for example, or less confusing ways to model things. So the ability to change the schema is, of course, challenged by existing clients of the old schema and then migrating them onto the new one. That's a really hard problem. It's often tempting to put information into strings. I think all of us probably have seen cases where there's information about an adjacency that's embedded in the description of a port, for example. And so, the model gives us an opportunity to really get away from that sort of approach and introduce explicit attributes to capture that information rather than trying to put them in strings. So we did have to do a little bit of cleanup to remove those cases from the model, although we probably still have some. Another hard lesson we learned is that we really should have used UUIDs, I think, for entities. We started out by using human readable names for entities, which made things a little bit more brittle. And we talk a little bit more about this in the paper. I'd urge you to take a look if you're interested. And then, maybe obvious, but it's worth stating here, is that the cleanest or most elegant schema will not save you if you don't have, clean data to put into it, right? So populating the model with the data, bootstrapping the model is a challenge that should be considered when you're attempting something like this. So I'll talk a little bit about these last few things and then wrap up. So schema design, just quickly, I'll say that we found that fewer entities doesn't make for a simpler model. So we started out thinking that if there's too many entities, it'll be hard for people to kind of look through this long list of entities and figure out how to capture what they're trying to model. But fewer entities actually resulted in us, creating different types and overloading a particular entity with too much information that then made it hard to reason about the right way to do the modeling. So our kind of approach now is to bias towards more entities that make explicit kind of what it is you're trying to model. And the way that we make some of these decisions is to think about orthogonality and separation of aspects. So orthogonality just means that if these two things that you're thinking about modeling and trying to decide whether they should be in a single entity or separate entities, if you look at the relationships of the two things independently and the attributes, if there's a lot that's shared or common, they probably should be the same entity, maybe with some attributes that let you distinguish. But if they really are mostly disjoint, then they really ought to be in two different entities. Maybe it seems like a straightforward idea, but we did struggle with kind of figuring out whether it's best to create new entities or reuse existing ones. Separation of aspects is similar. It just means essentially taking a very complex blob and instead of sticking it in a single entity, separating it out. And so an example of where we've done this is like in devices, where we separate out data plane components from control plane components to make the entities a bit more manageable. We bias towards explicit relationships rather than name-based attributes. So instead of sort of embedding attributes that identify what may be on the other end of a relationship, we want to use the relationships directly. It makes the traversal and retrieval easier. There are some trade-offs though that we talk about in the paper. And we also found that, relationship kinds don't always fit well. So a contains or traverses relationship, for example, it may not be always clear which relationship is the right one to use to capture the concept that you're trying to model. So it becomes critical to make sure that we're doing our best to use them consistently so that people, when they're writing queries, kind of can predict what they're going to get. Schema evolution, this has been a hard thing. We have constantly been adding to the schema. We use a few different ways to manage the evolution. One of them is to have kind of a review board, set of experts who kind of curate the model. So proposals to add new concepts to the model, new entity types, et cetera, go through this review board. And our job in the review board is really to make sure that there's some consistency of concept, that we're not reinventing something that may be already in the model, or not suggesting to reuse something where it's really more appropriate to create a separate entity. Those kinds of decisions are made in the review board. We've introduced this notion of profiles to help define a constrained definition of a model to make it easier for producers and consumers to evolve. So as you, for example, let's say we take the cluster fabric or the data center fabric network, and we've defined a sequence of profiles that have evolved the model, but clients can write their software against a certain profile version, and producers can make sure that when they produce a version of the model, they're producing it according to a profile so that clients can have some predictability in what to expect in the model. And the profile defines things like what entities, what relationships are valid, what attributes should be present, et cetera. And then I already talked a little bit about CAN queries. And I'll just say that, abstraction is important and easy, but taxonomy, in other words, classifying the different concepts into these modeling terms is really hard, even for people who are experts in the network structure. And then lastly, we have biased towards this notion of a data flow pipeline versus a database approach. And all that means is that since we kind of build these different versions or different types of models and then versions within them, it becomes much easier to manage producer-consumer interactions when you have a data flow that basically says, some high-level design software system is producing a high-level design model. There's some other lower-level design software system that can consume that high-level design model and produce its, let's say, lower-level design model. And then there might be even another layer, let's say from layer 3 to layer 1, that consumes the L3 model and can produce the L1 model. So, there's clear ownership of who is producing versus who's consuming. There's clear APIs between the different software systems in terms of the kind of model they're expecting to get and the kind of model that they're expecting to produce. It makes it much easier than this approach, for example, where it's much harder to kind of reason about ownership of the data. It's much harder to create test instances of data to test our software systems when you have all of it in a single topology database, and all of these different systems are just accessing the things that they think they need from the topology database. So we've biased towards the left-hand side of this picture, which is more of a data flow approach than the database for that reason. So that brings us to the summary. A few quick things to leave you with. We've seen that automation requires modeling at multiple layers, because automation is operating at multiple layers, all the way from capacity planning and forecasting, down to configuring every aspect of a network. The abstraction and taxonomy, as we mentioned, is hard, and it requires some thinking about how to evolve the model in a controlled way that makes it possible for software to evolve with it. We couldn't get away with just defining the data model. We had to build a fairly complete software ecosystem around it. And as I said, we've adopted these network models across almost all of our network management automation at this point. So it's fairly well embedded into our network operations. And then we are using the models, of course, to represent not just the current as-built version of the network, but also future versions, such that we can model the entire life cycle, not just the current running network. So with that, thank you very much for listening, and I'll be happy to take any questions.
So that was fabulous, Anis. Thank you so much for providing us that information. We know that automation is one of the most requested topics on the NANOG surveys that we give, and having an overview of how you guys are, and one way that you guys are approaching this is really valuable to NANOG as a community. So we definitely had a couple of questions that came in. The first one was from Ernest. He said, thank you for the presentation. I wanted to ask you the tool you use for network capacity forecast.
So network capacity planning and forecasting is all kind of, it's an internal tool, so it's not something that we're using off the shelf. It's very tightly integrated with our overall kind of network optimization framework, which takes traffic forecasts from our different product areas. It takes information about the physical infrastructure and the network structure, which comes from the MALT models, information about failure rates and so on, and costs of equipment, things like that, and sort of produces layer 1 and layer 3 topologies along with their link capacities. So we don't, like I said, we don't use something that's kind of readily available. We've spent actually quite a bit of time iterating through our capacity planning and optimization pipeline. So in relation to this talk, I'll just say that, those systems all use MALT as one of their key both inputs and interchange formats between different stages of the optimization. So in that sense, it's quite tightly coupled to what we talked about here today. I'm sorry, I can't say too much about it just because it's an internal system. I'm not sure how useful it would be to get into too much detail there.
That makes sense. Thank you for that answer, though, what you could provide. So Gordon asked, hey, Anis, do you recommend that a system similar to MALT could be implemented in a network ecosystem like Google's, meaning not every single bit of the network stack is deployed and maintained by the same org?
Yeah, that's an interesting question. I mean, I think that Google is big enough with enough different teams working on different parts of the network that it often feels like it's different organizations working on different parts of the network. And in fact, this is one of the key reasons why we came up with a common schema like MALT in the first place, to enable a common language for talking about the network structure and its attributes. So it's proven extremely valuable to have a common interchange format that lets what are essentially different organizations exchange information. So if you were now extending that to, let's say, beyond a single company, then we can say that same thing applies, right? If we've in fact contemplated how we might expose parts of MALT, or maybe a modified version of MALT, to, let's say, external customers, where they could describe things like virtual topologies using that and have it consumed by some of our provisioning systems, for example. And so there's some benefit to having this common interchange. So I think it does apply to organizations that aren't like Google. In fact, we use it across different teams that are building different parts of the network, especially where the seams of the network are, where things come together and you need a common way of expressing what's on either side of that seam.
Okay, thank you. So Tony asked, how do you think or handle temporal issues? For instance, labeling things as future versus present, or even past, and state intent that's temporary. So for example, a link that's been costed off intentionally during a maintenance, which means it's in the correct intent, but short term.
Yeah, great question. We basically evolved the model. As I mentioned in the talk, we do use models for different stages of design and deployment. So one simple example is, we use entirely different models, for example, to represent the network at 3 months out, 6 months out, 12 months out, and then a different version of the model, or even a different schema to a large extent, that represents the as-built model, or the currently configured model, network rather. We also use this mechanism called entity states, where suppose you have an entity like a device. It goes through its own life cycle in terms of its turn up. When it's just part of a design, then it becomes provisioned, like installed, actually instantiated somewhere physically. Then it becomes provisioned with its initial configuration. Then finally, maybe it's ready to start serving traffic. So we actually label entities that go through that kind of life cycle with this notion of entity states, so that a consuming software system can sort of see where in the life cycle a particular device is. The last part of the question around maintenance is interesting also. So we tend to, at least for our B2 network, tend to reflect the temporary states in the as-built model as well. So in other words, suppose that we take some link offline because it's under maintenance, or we have drained line card on a device, some ports aren't available. They'll be marked as such in the model, so that any system that's going to, let's say, run a workflow where it depends on that link being available, or the device's current status, can use the model to see what the current state is. So we do capture some of that in the as-built model in those cases. So I would say we have a few different mechanisms for handling temporal concerns. One is just different versions and even schemas of the model that represent the network at different points in its overall life cycle. And then we have entities themselves, like devices, links, etc., that have their own entity state that tracks its life cycle over time. And then we, do represent some forms of operational state, like whether a particular entity is drained, for example, in the as-built model itself. Hopefully
Gotcha. That makes sense. Thank you. So Paul asked, he said, great talk, Anis. He asked, can you share the size of the teams working on Malt, the pieces you focused on first, and how long it took from the initial concept to having a MVP of the most valuable player of the ecosystem?
Yeah, so getting to an MVP, probably, I guess when I joined Google it was beginning of 2014, and Malt was already kind of conceptualized by that point. But the focus was a little bit different. So as I mentioned, our initial use case was around configuration management. And so we started really building out the schema to support an intent-based configuration scheme around that time. And it took us, I would say, probably 8 months or a year, 8 to 12 months to get to a point where we had something that could actually be used by these consuming systems. So it took quite a bit of time and incrementally building it over time. So, for example, having a complete model that allows you to represent the entirety of configuration in a network as complex as B2, our user-facing backbone, did take us some time. The size of the team has grown also considerably. So I would say that we still have a relatively small team managing kind of the core schema itself. I happen to sit on the review board I mentioned, and there's half a dozen of us representatives from different parts of the organization, that work on different network environments that are representing kind of the perspectives of each different consumer, so that as the schema evolves, we can still rationalize about them. The development team is sort of split into different sections. So we have a development team that's devoted to primarily use cases, tools. A lot of the development work is around the libraries, the query support, all the software systems that go with the schema itself, not necessarily with Malt, the core of Malt. And those teams, I would say, are on the order of, probably 15 to 30 people, for our data center fabrics with the very complex models, and maybe a little bit less than that in other parts of the network. But the core team that maintains the schema and the core schema tools, the visualization, the storage system, etc., I would say it's probably on the order of or 10 people, roughly, maybe less than that.
Gotcha. Thank you. So Tom asked if you could post a link for the paper you mentioned that goes deeper into the topic. And I'm not, maybe you already did that actually in the in the chat room?
Yeah, happy to. I will add that. I was kind of hoping the slides would be available at the time of the talk. So I did put a link to the paper on the front page of the slides also, just FYI. So when those become available, you can get them there as well.
Great. Thank you.
I will add a link.
Okay. So Chris asked, what modeling language did you use, and is it published?
The modeling language is sort of we basically represent the schema as protobufs internally. So we don't use a separate modeling. We didn't define a new domain-specific language just for the model. We basically defined the schema as a set of protobufs, and that allowed us to use a lot of our tools, and especially tools across different languages, to work with the models. We get asked a lot about open sourcing the models and the tools. At this point, I think the ideas around Malt are probably quite valuable for the external community. The problem is that the specific implementation and even the schema that we have is so tightly coupled to Google's network infrastructure and our network structure that it becomes hard to disentangle, kind of the core schema elements from some of the specifics that we have in our environment. So I think it's a significant amount of effort, but one that we are interested in, and we're still trying to figure out how best we can make some of this available externally. But right now, I unfortunately don't have a lot more to say about plans to make it available open source. Okay,
thanks. So Ed asked, where did the inspiration come from to attempt this?
Yeah, interestingly, this grew out of an effort in the network architecture team just before I had joined. I think the idea was that we had all these systems that were trying to operate on the network, especially the physical entities of the network. So the Malt started out as a schema that was really representing kind of physical things like buildings and cables and conduits and stuff like that. And we sort of evolved it over time, thinking about other use cases into really more a topology model. We need a way to represent topology. We had N of them at the time, and we needed a single one. Once we started representing topology, in other words, interconnections, it quickly became apparent that people want to represent not just the topology, like connectivity of different entities and devices and links, but also attributes about them, how they're configured, then how they're designed and planned. So I would say that the evolution and sort of inspiration for kind of building out this infrastructure and ecosystem has really been driven by, I would say, the vacuum that we had in terms of a common structure, a common storage system for all these models. Once you have something like this available, people, engineers will think of all kinds of use cases for them. And just earlier this week we had our review board meeting, and there were a number of new proposals for people wanting to add things into the model that we hadn't thought about before, because they have some system, the information is available there in Malt, or it can be added to Malt in a convenient way, and so the set of use cases just keeps growing.
Yeah, that's awesome. And we definitely see that every time when something new comes out, it kind of inspires thought and a rippling effect. It's really neat. That's great. And then the final question that we have in the Q&A section is from Travis. He said, is there an API interface that you use to manage the tool?
Yeah, that's a good question. I mean, I'll maybe reinterpret the question slightly, and Travis, invite you to ask it differently if I'm not answering it. Kind of the developer view of the model, or the API that we use. Let's say you're writing a configuration generation system, and all the intended configuration information is in the model, and so you basically just want to get the data that you need out of the model and put it in some data structure that then you can manipulate and use to build your, let's say, business logic for config generation. And so we don't have a single API as such, unless you count things like the query language for just querying the model to, let's say, traverse the topology, or query, how many BGP sessions do we have with this particular ASN. Those kinds of things we can address through the query API. But we've built a number of specific libraries that give different use cases, or different engineers who are working on different use cases, fairly specific view of the model. Like if I'm building configuration for a device, we have a library that will, traverse the model, collect the data about the device, its adjacent links, its interfaces, its ports, put all of that into a data structure that then makes it easy to access that information. So when I'm building out config gen logic, it's sort of all in one place. So that becomes the API that config gen writer for, let's say, the B2 network would use when accessing the model. So I would say we don't have a single API that way. We have sort of a few sets of APIs that we use depending on what the use case is.
Okay, thank you. We have one final question from Ed. He said, or he asked, if possible, have graph database concepts been of interest in your designs with topologies?
Yeah, I think at the time when we started, graph databases, if you think about, open source graph databases like, let's say, Neo4j or technologies like that, they didn't quite have the support we needed, in particular around kind of versioning models. Like, we're trying to track life cycle by just creating new versions of models and making them available to different producer and consumers. And it wasn't really, nothing like that was really available. And in addition, I would say that we were kind of very easily kind of convinced to use something like Spanner, where we have this globally distributed database with transactional semantics. It works at scale. It's resilient to failures. It's replicated. All of that happens sort of under the covers, and it was a natural choice to kind of use that as a way to store what is in effect a graph model as an entity relationship kind of schema. And so we did have to do some work to massage that entity relationship model, which is a graph model at its essence, into a SQL database. So I would say you could argue there's some impedance mismatch there, but on the other hand, as I said in the talk, we decouple kind of the schema that users see from the underlying SQL schema, and we get all the benefits of something like a global spanner. And so that's why we hadn't really experimented or investigated a ton with other off-the-shelf graph databases when we started this work.
Gotcha. Well, that was the end of the questions that came into the Q&A chat window. Before we kind of wrap up, did you have anything else that you wanted to add, Anis?
No, I think I'll just echo what Liz said at the outset of the Q&A period. This is sort of one perspective on doing this. I think there's lots of different approaches, and whenever we talk about standardizing a way to represent topology models, most network operators, certainly the larger ones, have their own kind of approach and scheme for this. So, it becomes hard then to think about what a single standard, let's say, across the industry might look like. But I think it is something of interest to talk about. But, again, this is sort of our experience and some of the problems that we had to solve as we see this sort of rapidly growing set of use cases around modeling. And I just want to also thank everyone for the interest in the talk and the topic, and thanks very much for all the questions.
All right, thanks, Anis.